Okay, you guys. So we talked about IMFs yesterday. And the reason why IMFs are so important is because they determine properties, right? Like we've done all of this big mess from Lewis structures to ball and stick models, the geometries affecting the polarities, because the polarities tell us about the IMFs and the IMFs tell us about the properties. So we've done all of this work just to get really to this point of being able to predict behavior of substances based upon their intermolecular forces. So the IMFs that we talked about yesterday were dispersion, dipole-dipole, and hydrogen bonding, in that order from generally weakest to strongest. Also, ion dipole attractions when something dissolves in water. And these are the IMFs that determine the properties of covalent substances. The properties of ionic and metallic and covalent network solids, those are determined by their relative structures. So remember, keep in mind, these are properties of covalent substances based upon the strengths of their intermolecular forces. So what are the things that we're talking about, right? Well, obviously state of matter. And we're going to talk more about state of matter when we look at phase change in the end of these notes. So you can see I'm kind of jumping around the textbook a little bit. I'm going to talk 11.3 and 11.5. And then I'm going to, at the end of class, talk about 11.4, which is phase change. So IMFs will affect all of these properties that are listed below and state of matter, okay? So the first set of properties that I want to talk about are melting point and boiling point. And you already know what melting point and boiling points are. They're the temperatures at which a solid turns into a liquid and a liquid turns into a gas. But we're going to add to this definition because now you know more. Now you know that pressure also affects melting point and boiling point. It's not just temperature that affects state, it's also pressure. So when we say melting point and boiling point, it's kind of understood that we are talking about the normal or the standard melting point and boiling point of a substance. When I say normal, I mean, it's totally arbitrary what we decide to call normal. And standard is often denoted with this little not symbol, like a degree symbol. We have defined normal as 1 atmosphere of pressure, which is the pressure at sea level. So, you know, sorry, people at higher altitudes or lower altitudes, that's not considered normal pressure. So when I say that the melting point of water is 0 degrees Celsius, that's the normal melting point of water. So let's see here. What did I want to do? So normal pressure of the atmosphere, P naught of the atmosphere, is considered to be 1 atmosphere of pressure. And the normal melting point of water is 0 degrees Celsius. This is for water. And the normal boiling point for water is 100 degrees Celsius. But later this week, we're going to look at how pressure can affect and change these melting points and boiling points. Okay, so that's just our definition. What I want to talk about today is how do intermolecular forces affect melting point and boiling point? And don't memorize these things, you guys. Like, just think about them. IMFs are the things holding samples together. So if you have like a strong IMF holding those molecules together, they're going to be harder to melt and harder to boil. So they're going to have higher melting points and boiling points. So I'll just do my effects here in a different color. So if you have, if you have strong IMFs, you're going to have higher melting points and boiling points. And obviously the converse is true as well. Converse, is that even a conversely? The inverse is true as well. Ignore me. Okay, so if you have weaker IMFs, you're going to have lower melting points and boiling points, but I don't think we need to write both options there. Okay, now this is just a temperature value. like this is like a degrees on our thermometer. This is not how much heat is needed to get to that temperature. Okay, so it's not the amount of heat, it is just the target temperature at which this phase change occurs. We're going to talk about how much heat is needed a little bit later on. Any questions about melting point or boiling point? Okay. Next property is viscosity. Fancy definition: resistance to flow. We only talk about flow with fluids or liquids. So this is a property only important when we're talking about liquids. You can think of resistance to flow as stickiness. That's the not fancy word. Right? So something that is highly viscous would be like honey or molasses. Something with strong IMFs, something that really wants to be stuck together, is going to be highly viscous. Strong IMFs equals higher viscosity. The reason why honey is so sticky and caramel is so sticky and really viscous is because those sugars are big, long carbon chains, lots of surface area, lots of dispersion forces, strong IMFs, highly viscous. But in addition to the intermolecular forces affecting viscosity, temperature also affects viscosity. So when you increase the temperature of something, what happens to the viscosity of it, do you think? And I'm not looking at you, so just unmute yourself and tell me. When we heat something up, does it become more sticky or less sticky?
It becomes less viscous.
Very good, thank you. A couple of people there. Okay, so with an increase in temperature, you get a decrease in viscosity. And don't memorize these things. You guys just think about what you know. Like you put that olive oil in the pan, and it's like pretty thick, and it kind of like stays in that pretty little pattern that you put it in the pan. You heat that oil up, and it spreads all the way out. And that makes sense, right? Because if you add kinetic energy, you add heat, you add kinetic energy, you make those molecules move faster. They're able to overcome those high IMFs that they have, and it's able to spread out throughout the pan. Okay, moving right along. Another property that we only talk about with respect to liquids is surface tension. And this is the attraction of molecules at the surface of a liquid to its neighboring molecules and those beneath the surface. And you're like, well, isn't that just IMFs? Like, yeah, it's just IMFs. But it's making you visualize a molecule on the surface being attracted to the molecules next door and the molecules underneath. And so this attraction side to side and downward creates some tension there. It creates this pulling effect and builds some tension on that surface. The stronger the IMF, the more surface tension you're going to have. You may remember doing this little experiment with me last year, or maybe you did it in middle school, where you like take a penny and you drop water droplets onto that penny, so like if you have a penny like this, you drop water droplets onto it, all of a sudden you get this like big bead of water. Like the water does not fall off of the penny. It just sits there like a big, I mean, eventually it does if you add too much, but you can, when you look at it at eye level, you've got this really big bead right there. And the reason for that is because those water molecules have really strong IMFs. Those hydrogen bonds in the water, that perfect hydrogen bonding we talked about yesterday, creates this surface tension here where the molecules are attracted to each other side to side and inwards, allowing this water to bead up like that. If you do the same thing with, a non-polar substance like oil, it'll just like falls right off. Very low surface tension with less intermolecular forces. It also allows, like spiders to run across the surface of the water because of that tension created. Okay, any questions? All right, let's talk solubility. Solubility is obviously the ability for a solute to dissolve in a solvent. And we've used solubility a lot, right? Like we have our solubility rules, which help us predict how soluble something is. But the reason why something is soluble or something is insoluble in water would relate to the strength of its intermolecular forces. And not just the strength of the intermolecular force. This is what's a little bit different with solubility. It's not about strength, it's about type. Okay, so the type of the intermolecular force that's present determines whether or not things can mix. You got to think, right? Like for this thing to mix with this thing, they've got to have some attractions for each other. So you have to have similar IMFs in order for something to dissolve. The real sort of like easy little moniker we give this is like dissolves like, which means if you have something that's polar, it will dissolve in something that is polar. If you have something that is non-polar, it will dissolve in something that is non-polar. So if it's got dispersion forces as its predominant force, it'll dissolve in a non-polar solvent that has dispersion forces. If you have a polar solute, you need to dissolve it in something that also has dipole-dipole or hydrogen bonding. You can also, another like dissolves like, is ionic solutes will dissolve in polar solvents. That doesn't seem like they're the same thing, but it is. Ionic has charge, positives and negatives. Polar, partial charge, partial positive, partial negative. And so here, you're going to get those ion dipole attractions that we talked about yesterday. So solubility, very dependent on IMF. Okay, so whoops, I was supposed to be doing these things in blue. So it's not necessarily strength of IMF, but type, right? Here's the factor we have to account for. Like dissolves like. Just as temperature affects viscosity, temperature also affects solubility. Listen, all of these things are going to be affected by temperature. Well, not melting point and boiling point, those are temperature values. All of these things are really going to be affected by temperature because temperature can help overcome those IMFs. So if you have something that's sort of like determined by IMF, temperature is going to affect them as well. Now, in terms of solubility, temperature affects a little bit differently because when you heat a solvent, it expands and makes more room for something to dissolve. So you can increase how much stuff you can dissolve depending on temperature. Okay, so temperature, with an increase in temperature, you also get an increase in solubility. More solute can dissolve again, that has more to do with the fact that you're making more space to put more of that solute in, and you can create more surface area in that solvent to have attractions between the solute and the solvent. Okay, that's why like dissolves like, because your solute attracts to solvent. Okay, so that's all review. Here's something new. Not entirely new. In fact, we used vapor pressure values. You guys had to look up vapor pressure values for the molar volume of a gas lab, right? The lab that we did before break. You had to look up how much water vapor pressure there was up at the top of that udiometer. So it's not entirely new, but we didn't really define it. So let's go ahead and define it, and then I'm going to give you guys a diagram to help you better understand it, because the definition is kind of wordy. Okay, so vapor pressure is the pressure exerted by the gas phase of a substance when it is in equilibrium with the liquid phase below it. We're going to talk about what this equilibrium means and give you a diagram here in a second. So go ahead and write that down, and then we'll draw it out, which will make it make more sense. Okay, so let's say I have an evacuated container, meaning nothing in there, the vacuum, no air particles in there. And I add some water to the bottom of my container. What's going to happen here is some of these water particles that are at the surface are going to naturally escape and fill this vacuum or fill this void as water molecules in the gas phase. So you're going to have some liquid water turning into water vapor. Now, there's going to be all of these collisions of water molecules with each other and the sides of the container. That's the pressure that I'm talking about. So there's going to be a measurable pressure up here of this gas phase. That's your vapor pressure. Now, what do I mean by in equilibrium with the liquid phase below it? Well, enough water vapor has to evaporate to sort of fill up that space, if you will. But some of these particles, when they collide back with the liquid phase below it, are going to condense back down into a liquid. And for every one that condenses back down into a liquid, another will evaporate up into the gas phase again. So you're going to get this, we call it dynamic equilibrium, where the numbers that are condensing down are equal to the numbers that are evaporating out. Okay, so this is a dynamic equilibrium. And however much pressure there is measured up here at the top is what we consider to be the water vapor pressure, or for any liquid, the vapor pressure at whatever temperature you're at. Okay, so up here, the pressure of this gas above the liquid is equal to the vapor pressure. This vapor pressure also depends on temperature. So this is at a set temperature. So remember, temperature. When you guys were looking up these values for the lab, everybody had a different value because you were looking up whatever the water vapor pressure would have been at your particular temperature. Okay, and so let's think about how temperature would affect this. If you have an increase in temperature, the liquid is going to be more likely to become a gas. So with an increase in temperature, you get an increase in vapor pressure. But I have not yet talked about strength of IMF. The stronger the IMF, again, don't memorize these, think about them. If it's got a strong IMF, it wants to be in the liquid phase. It's going to be less likely to become a gas. So the stronger IMF you have, the lower the vapor pressure. And obviously, the weaker the IMF, the easier it is for something to become a gas. Now notice, I'm not talking about full-on phase change here. I'm not talking about all of the liquid boiling and becoming a gas. Temperature, with or without addition of temperature. I'm just talking about the particles at the surface, and we still do have a liquid phase. I'm just talking about the particles that are at the surface going into the gas phase and condensing down into the liquid phase in dynamic equilibrium, such that there's actually no change in how much liquid versus how much gas you have present, okay? It's not phase change here. It's just the particles that are at the surface, okay? When we're talking about these particles doing that at the surface, this is, we don't say it's boiling, we say that it's evaporating. Okay, so evaporation is when the particles at the surface of a liquid transition to the gas phase. The difference between evaporating and boiling is when the whole entire thing is undergoing phase change. So for water, that would happen at 100 degrees Celsius, but at 25 degrees Celsius, you're gonna have some evaporation that happens. And if that container is closed, you get that vapor pressure up at the top. If the container is open, eventually all of that water is going to evaporate. So to measure this pressure, this would obviously have to be a closed container. Okay, so I get into so many arguments with Austin Chang about this because I think like on a test once, I was referring to vapor pressure and he was referring to volatility, and like we used different, these two words are related, but they don't mean the same thing. And so he gives me mugs that say volatile because we like argue about volatility and vapor pressure. He's so silly. It's like that's super glued on there. I can't even take it off. Anyway, he's so funny. So you guys can go talk to Austin about vapor pressure versus volatility. What I will tell you that he will not, because he's stubborn, is that vapor pressure is a quantitative value. It's a noun. It's like a measured amount of how much gas is up here, basically. It's not moles, but it's related to moles of gas. The more moles of gas you have, the more pressure you have. It's a quantitative measured value. Volatility, oh, this looks like I defined, look, see, this is maybe why I confused Austin. That definition, you guys, was for vapor pressure. Volatility is the ease at which this is all squishy, substance evaporates. Okay, this is not a quantitative value, it's qualitative. It's an adjective describing a substance. Okay, so if you have strong IMFs and low vapor pressure, we say that means that this thing cannot easily become a gas. It is not volatile, non-volatile. So if we wanted to talk about this in the inverse, we would say if something had a weak intermolecular force, okay, so fine, here, I'll do a full inverse here. If we have a weak IMF, we're gonna have high vapor pressure, meaning like it's really easy for that substance to evaporate into the gas phase. You're gonna get a lot of vapor pressure. And we say that these things are volatile. And highly volatile things also tend to be very smelly, like alcohols. The reason why you can smell something if it's volatile is because you're actually, when we smell something, we're smelling the gas phase of that substance, right? Those gaseous particles are actually going up into our noses and being sensed by our nervous system. Okay. Do I want to talk about anything else here? I don't think so, but I'm going to pause and check in with you guys. All right, so phase change. Let's review some things we already know. Let's draw some diagrams. Solid. The AP exam loves diagrams. Okay, now listen, I always draw my liquids just at the bottom of the container. Like I don't usually like fill my container with liquid. Sometimes the AP exam will like fill the container with liquid. And you're supposed to know that that is a liquid and not a gas because it just looks more crowded. Like a gas for the AP exam would look like this. Liquid, gas. Okay, so I just wanted to make you aware of that because I was looking at some problems the other day and I was like, they think that's a liquid? I mean, if you were comparing those three things, yes, obviously. But oftentimes I always just draw my liquids at the bottom. So I didn't want you guys to be confused. All right, so solid, liquid, gas. Weak IMFs, nope. Strong IMFs, weak IMFs. That's if these things were different substances. Let's say these are all the same substance. Let's say this is water. If we want to go from solid to liquid to gas, we have to add heat. We have to add temperature or reduce pressure. We'll talk about that later. So let's talk about what the names for these phase changes are. Solid to liquid, we already know. We know all of these. Melting. Liquid to gas, boiling, or vaporization. Not evaporating though, because that's just the surface. Okay. However, these things can also happen in reverse, right? So gas can go down into the liquid phase, and we call that condensation. And we don't often think about it, you guys, but condensation happens at the same temperature that boiling happens at. You're just talking about a different direction, okay? So don't think like when we say that the boiling point of water is 100 degrees Celsius, that is also the temperature at which the gas is condensing back down into the liquid, okay? Same thing goes here, liquid to solid, this is freezing. So yes, water freezes at 0 degrees Celsius, but it also melts at 0 degrees Celsius. It's the same temperature, it's just direction. Now remember how I said temperature is the point at which this happens. Okay, so like the melting point and the freezing point of water is 0 degrees Celsius. However, there is an amount of energy associated with the actual process of melting something or freezing it. So yeah, this process happens at 0, but how much energy is required to overcome those IMFs and actually separate the particles? That amount of heat is called the delta H of fusion. So delta H fuge. Now I put it in between because it's like the same, like I said, it's the same amount. It's either endothermic going that way or exothermic going that way. The amount of heat needed to boil something, or in reverse, take that heat away to condense it, is the delta H of vaporization. And again, right, like going this way, endo, add heat to a substance to get it to go solid to liquid to gas. Going in reverse, you got to take that heat away from that substance. That substance has to release heat to go from gas to liquid. The substance has to release heat to go from liquid to solid. People always have a hard time thinking about those processes as exothermic. I don't know why, because they think like, no, but freezers are cold, so it can't be exothermic. But you're not thinking about it. For a liquid to become a solid, it has to get rid of some of its heat. It has to get rid of some of its heat. So it's the process is exothermic. Okay, and of course I'm leaving out, I haven't yet talked about solid to gas, right? Solid to gas going this way, the endothermic process, we call sublimation. And the reverse, gas to solid. The exothermic version of this is called deposition. And the amount of heat to go here to here, delta H, sublimation. It's snowing a little bit. Okay, any questions on this vocabulary? Okay, let's draw a diagram. This right here, you guys, is called a heating curve. Oops, a heating. Whoa, pen, chill. Okay. What's happening? A heating curve, okay? And it only looks at temperature. You'll notice if you look at this curve here, on our, go ahead and draw this, on our y-axis, we have temperature, and on our x-axis, we have time, or heat added, right? Because we are adding heat throughout this whole process. So I want you to say time, also maybe put heat added over time. Okay, so let's imagine, if we will, that this is the heating curve of water. And let's say that my heating curve is starting off at point A at like, let's say, I don't know, -10 degrees Celsius. And what we see happening here as time goes by is I'm heating this ice, right? So if we're at -10 degrees Celsius, this is obviously going to be ice because we know that the freezing point is 0 degrees Celsius. So if we're below that freezing point, it's going to be solid. So we're adding heat, adding heat, adding heat. And what we see happening is the temperature of the ice is going to increase. You know, so from A to B, we're getting this climb or this increase in temperature. When you have a change in temperature, what you have here for your solid is a change in kinetic energy. You're warming up the solid. The particles of the ice are vibrating faster and faster and faster and faster and faster and faster. And then all of a sudden you get to point B and you're still adding heat, but the temperature stops changing. And you're like, is something wrong with my thermometer? Is my thermometer broken? Why isn't the temperature changing? Nothing's wrong with your thermometer. The temperature is staying the same because what happens here, and interestingly enough, this is at 0 degrees Celsius that this happens and you stop getting a temperature change, is that the energy that you're putting into that ice is no longer being used to increase kinetic energy, to make the molecules move faster. Now that heat added is being used to make those molecules move farther apart from one another, to overcome the intermolecular forces that are present. And so here from B to C, you're getting a change in potential energy. Where do I want to put this? Change in potential energy here, B to C. This right here, you guys, this flat portion of the graph is where your phase change is occurring. This is where it's going from solid ice to liquid water. And so all of a sudden, you're going to start to see your ice cubes start to melt. And you're going to have ice and water, ice and water, ice and water at 0 until the whole thing is water. And then all of a sudden, the temperature is going to start to go up again. And you're like, oh, my thermometer is not broken. And so the water is going to warm up, warm up, warm up, warm up, warm up. So this is where your liquid is warming. Here you have a change in kinetic energy again. You get to point D, all of a sudden, you're at 100 degrees Celsius. And all of a sudden, the temperature stays the same again for a while. But you start to notice bubbles forming. Here is where your liquid is turning into a gas. You've got your change in potential energy. This is where your phase change is occurring. This is your vaporization or boiling. All of that liquid water has gone into the gas phase and temperature starts to rise again. Yes, you can heat a gas, and those gas molecules move faster and faster and faster and faster, and you start to see the temperature rise beyond 100 degrees Celsius. You're starting to change kinetic energy again. Now, again, this is looking at it going in the endothermic direction, like left to right. If we were going right to left, you could look at the same amount of, you could look at the same thing, be looking at, well, how much, heat is needed to be taken away to go from gas to liquid to solid. So we can look at the temperature changes associated with the reverse process as well. And again, here at 100 is where it's going to condense, and here at 0 is where it's going to freeze. Okay, so these flat portions, you guys, this is where phase change happens. This is where you have changes in potential energy. Where the curve rises, where you have a slope here, you've got changes in kinetic energy. And this is very important because if I ask you to calculate how much heat in total is required to go from, like, let's say this point on my graph to this point on my graph, we need to know what kind of temperature changes, not temperature changes, what kinds of energy changes are happening so that we can do these calculations. So let's say that this random point that I picked here, I don't know, what does that look like? Let's say -7 degrees Celsius. And like, let's say this point up here is like 104 degrees Celsius. So my question to you guys is going to be, let's go ahead and write the problem down here below. How much energy or heat is required to turn 35 grams of solid ice at -7 degrees Celsius into water vapor at 104 degrees Celsius. All right, how much heat is required to turn 35 grams of solid ice at -7 into water at 104? All right, well, let's take a look at our graph here. Here at -7, I've got this change in temperature up to 0 degrees, right? So I have this segment, between A and B, where I have a change in temperature. I have this change in kinetic energy. Well, if I have a change in temperature, I can calculate how much heat is required to do that using Q equals MC delta T, right? If I have a change in temperature and I know how much stuff I'm trying to heat up, and I know the specific heat of that substance, I can calculate how much heat was required to warm up the ice from -7 up to 0. So let's do that calculation first. Let's do that little green segment. Q, so we'll call this segment number 1. Q equals MC delta T, the mass of my ice that I'm warming up. Now, this specific heat right here, you guys, this needs to be the specific heat of ice, which is different than the specific heat of water. It's lower. It's 2.03. 2.03 joules per gram degrees Celsius. Specific heats have to do with the structural alignment of that substance. So like ice, when it's frozen versus water in the liquid phase, requires different amounts of heat in order to change the relative temperatures. So this is not 4.18, it's 2.03 because we're talking about ice. The temperature change that we're talking about here is from 0 to -7. So 0 minus -7 is a +7 degrees Celsius. We're talking about an energy input, so we should be getting a positive value here for the total amount of heat. Double check my calculations, please, you guys. Also, it makes sure that you're awake. All right. And 400, we'll go with 3 sig figs. I kind of did a random number of sig figs when I wrote the problem, sorry. 497 joules. This is just the amount of heat, you guys, needed for this little portion of the graph right here, just to warm up the ice. We also, we need to keep going though, right? Because this, I want to go all the way up to that point up at 104 degrees Celsius. If I want to know how much heat is required to phase change, to melt that ice, there's no delta T there. So I can't use Q equals MC delta T. I have to look at the delta H of fusion, right? Because remember, up above, we defined the amount of heat needed for phase change up here as heat of fusion, heat of vaporization, heat of sublimation. This is how much heat you need, not to make the molecules move faster, but to separate them, to separate that crystalline ice structure that we get when we freeze water. So I'm going to call this segment number 2. And I'm going to look up the delta H of fusion, which is a standard value for water, 6.01 kilojoules per mole. So just watch your units, you guys, right? Sometimes specific heats are joules per gram. Sometimes they're molar heats, joules per mole. Heats of fusion are almost always kilojoules per mole. So if I melted a mole of ice it would have, I would have needed to add in 6.01 kilojoules of heat. But I didn't melt a mole of ice. I melted 35 grams of ice. So let the units lead the way. Turn your 35 grams into moles using your molar mass of water. Then you can multiply by the 6.01 kilojoules per mole. So 35 times 6.01 divided by 18. 11.7 kilojoules. Okay, so these are two different types of calculations. When we're warming and changing kinetic energy, we use our MCAT equation. When we're phase changing, there's no change in temperature. We need to look at heats of fusion or heats of vaporization or heats of sublimation. Okay, we're going to end up adding all these heats together, but we're not there yet. Now we're warming up all of that liquid water from 0 degrees Celsius up to 100. So here in this portion where we have that change in temperature, we're going to use Q equals MC delta T again. Because we have the change in kinetic energy, our specific heat is going to be different, and our delta T is going to be different. So let's call this segment number 3. Still 35 grams though. Specific heat of water this time, 4.18. Change in temperature. This time we're going from 0 all the way to 100. So my change in temperature is 100 degrees Celsius. Watch your units, we're in joules. Okay, so that's the total amount of heat needed to get your liquid all the way warmed up to the 100 degrees Celsius where we're going to have phase change again. So if we go back up to our diagram here, no delta T, but we're still adding heat, right? There is heat being added. What is that heat being used for? It's being used to vaporize it. So here we're going to use delta H of vaporization, which again is just a standard value. We'll call this segment number 4. Our phase change. 40.67. Notice how much bigger the heat of vaporization is versus the heat of fusion, right? Solid to liquid, not as hard to do. Liquid to gas, a lot harder to do. There's going to be a lot more space, like way more significant change in potential energy here from liquid to gas than versus solid to liquid. Like you're completely overcoming the strength of the hydrogen bonds in order to turn something into a gas versus, ice to liquid water, those hydrogen bonds are still pretty significant. So again, we just need to go grams into moles. Right, once we've sort of thought this through, then it's just applying new values. 40.67 kilojoules per mole. I got 79.1 kilojoules. Because I'm a real jerk, I didn't end there. I did another little bit. I asked for even more. And these problems, you guys can they can pick any points on this graph. Like some of them will be really simple. You'll only have to do like 2 portions, 2 line segments, but I wanted to show you all the different possibilities here. So we have one last little segment to do from point E, 100 degrees Celsius, up to the 104 degrees Celsius. Of course, again, this is a change in kinetic energy. So we can do Q equals MC delta T again. But the specific heat is not going to be for solid ice. It's not going to be for liquid water. It's going to be the specific heat of water vapor. And that is our last segment. And then all we'll have to do is add them together. Man, I'm going to hit like right on time. Q equals MC delta T. Specific heat of water vapor is 1.84. Easier to change the temperature of a gas than to change the temperature of the liquid. And the delta T this time, what did I say? 100 to 104. So 4 degrees Celsius temperature change. $258 joules. Whew. So we're done. No, we're not. We have to add all these together because I asked for the total amount of heat needed to do all of this nonsense. So just watch your joules and kilojoules, shall we? I'm going to change everything to kilojoules. So 0.497, right? 1,000 joules in a kilojoule, folks. 0.497 plus 11.7 plus 14.630 plus 79.1 plus 0.258 equals 106 kilojoules. Needed to do all of that. Okay. So I'm going to turn off the recording.